Welcome to the final week of the class Neuronal Dynamics. Thanks for staying with me for such a long time. In the previous weeks, we have covered different aspects of neuron modeling. This week, we'll put the different strands together, and I hope I can show that we will arrive at some exciting results. The question I would like to ask this week is, actually, what is a good neuron model? And how can we compare a neuron model with data? How can we optimize parameters of a neuron model so that it really describes biology? So let's start with the first question. Let's suppose we inject an input current into a real neuron. The input should look like the one a neuron is likely to receive in vivo. Say, it has a fluctuating part, and suppose you suddenly see the image of the Sydney Opera House, the mean of the input changes, then you look at something else. So that's the kind of input current one could inject in a real neuron. The real neuron emits spikes. What I would like as a first condition for a good neuron model that if I inject the very same current into a mathematical neuron model, I would find the spikes at the same moments in time. But moreover, I could ask, well, in this region where there are no spikes, in the subthreshold regime, do the model and the neuron have the same kind of behavior? And then ideally, I don't want a model that's just a black box. Just a box where I get some input and an output. But ideally, I would like to be able to interpret variables in the model in terms of biological phenomena. Well, the model should be flexible so it accounts for a variety of firing behavior, and at the same time, the mathematical structure of the model should be such that there exists a systematic procedure to optimize parameters. Now, in week 1, we have seen a very simple neuron model. The neuron model consists of just one differential equation, and this can be described by some nonlinear function. And if you plot here the derivative du dt, then this means if this function f is positive, I have movement to the right. If it's negative, I have movement to the left. So this would be a stable fixed point of the dynamics. There's an unstable fixed point up here. If I apply a constant input, then the du dt curve is shifted vertically upwards, and I have no fixed points anymore. I have a flow that's always towards the right. And then if it hits this formal reset threshold, then we reset the voltage to some value UR, and the whole process starts again. So that's a nonlinear integrated fire model. And the first question is, compared to real data, now, what would be a good choice of this nonlinear function f? And we have seen in week 1 that there is a natural choice related to data. So one can extract this function f from data. We have also seen that one can try to extract this function f for more complex models. Let's review this first. Suppose in a first step we reduce a model like the 4-dimensional Hodgkin-Huxley model to 2 dimensions. That would be this system of equations. And we have seen in week 4 that we can analyze this in the phase plane, where the horizontal axis is the voltage and the vertical axis is this auxiliary variable W. Now what I've plotted here are the null lines. So this curve here is the U null line, and this curve here is the W null line. The arrows indicate the direction of the flux. And we see here that arrows are nearly horizontal. In fact, once the system is here, we know that it will continue along a trajectory which I can construct. And this trajectory, this detour, corresponds to a spike. So instead of each time modeling this trajectory in the phase plane, we can say, well, there is some kind of threshold. Let's call this the threshold, where we detect the spike. And then instead of integrating the two-dimensional differential equation, we just reset. Moreover, we see here that arrows are nearly horizontal. Why? Because the dynamics of W is much slower than that of the voltage. Normally, the membrane potential hovers around in the neighborhood of the fixed point, of the stable fixed point. That's where the resting potential is. And there's also a resting value of the auxiliary variable W. Now, if the input is big enough to kick it out of this regime, then it will start a horizontal flow. So we can say that during the initial increase of the voltage, W remains still close to its resting value. And that means we may assume that in this region here, just in this region, W is equal to W rest. We plug this back into this equation, W equal to W rest. So this becomes W rest, and the second equation just disappears. So now we have just one equation, a voltage equation, with some nonlinear function, and this is the function that's plotted here. Above the same range as before, and here I've indicated the threshold, the numerical threshold for reset. Once the voltage reaches this point here, we reset to a value UR, say this value here. Now the decision whether a spike is triggered or not actually happens in this region down here. So let's zoom on this region, and then this function looks like a linear curve followed by an exponential increase. That means the correct one-dimensional nonlinearity is a combination of a linear and exponential term. And this is called the exponential integrating Fire model. Alternatively, as we have seen in week 1, one can also extract this function f directly from data. If I divide the voltage equation by tau, I have this effective function f tilde, which is plotted here. And you see that the solid line gives a very nice fit. And the solid line consists of a linear term and an exponential. And that's true for different types of neurons. It's true for a pyramidal neuron. It's also true for the inhibitor interneuron. Thus, if we restrict ourselves to just one voltage equation and combine it with reset, the best function is the one that has a linear term and an exponential term, and this is called the exponential integrating Fire model. If the voltage reaches some value above this unstable fixed point here, say at this point here, we may reset the voltage and integration can start again. Thus, for one-dimensional neuron models, we can identify the best nonlinearity. It's linear plus exponential. It looks like this. This is called the exponential integrating Fire model. However, that's not sufficient. Such a model completely neglects adaptation, processes that happen on a slower timescale. It's impossible to use such a model to account for the diversity of firing patterns. There's a fixed threshold. However, we need to make this parameter theta somewhat dynamic. And then, this is a deterministic model. It has no noise. Now, these additional points will be discussed in the next lectures of this week. We'll get rid of these limitations. To summarize, thus, if we restrict ourselves to one-dimensional integrated fire models, then the best model is the exponential integrated fire, a linear term in the voltage equation combined with an exponential. However, this model has limitations, and we'll get rid of these limitations in this series of lectures for this final week. Please have a look at the quiz.